the terms of the sequence get closer and closer to the limit. But we make that more precise. We say exactly, we quantify exactly the rate at which it's getting closer and closer to the limit. So we say if you're given any small quantity epsilon, remember this corresponds to the radius of the interval surrounding the limit. So we think of epsilon as getting, for any small radius, for any small interval around the limit, there exists a point in the sequence. That point is represented by capital N there. There exists a point in the sequence, and every point after that, the sequence elements are that close to the limit. They're within a distance epsilon of L. Okay? So that's the definition, and that's definition 1.6 on page 6. And then we have this collection of 4 theorems. We proved the first two, 1.1 and 1.2, uniqueness of limits and the fact that every convergent sequence is bounded. We proved that last time. Today, we're going to prove the algebra of limits theorem. And so the algebra of limits theorem has 3 cases dealing with linear combinations, products, and quotients. Right? And it's saying that if you've got 2 convergent sequences, a sequence AN converging to A, a sequence BN converging to B, that any of these 3 ways of mixing them together, producing a third sequence, the third sequence will be convergent and it'll have the corresponding limit. So the linear combination of the 2 sequences will converge to the linear combination of the limits. The product of the 2 sequences, case 2, the limit of AN times BN, that converges to the product of the limits. And lastly, the limit of the quotient is the quotient of the limits, with the small proviso that we must avoid having 0 in the denominator. So the third case only applies when the sequence B, none of its terms are 0 and its limit isn't 0. Okay. And the tool that we're going to use to prove these is our formal definition of convergence. Okay. So without further ado, let's go into. So I'll be doing the working on the visualizer, and afterwards I'll scan these pages and get them up on the. I'll put it on both sides of the. Put it on both sides of the screen. So you've got the statement in your notes, which you can refer to, pages 6 and 7. Okay, so I'll scan in these pages afterwards and put them up on. Put them up as comments to the lecture videos. I haven't done it for the last one, but I'll do that this time as well. But I do suggest you make notes on the proofs as we go through, because it does help, I think, to connect, to help the ideas bed in rather than just passively watching them. Okay. So case 1 about linear combinations. Okay. So we'll assume we've got the two convergent sequences, AN and BN, as stated in the theorem. And we need to show that alpha AN plus beta BN converges to alpha times A plus beta times B as n goes to infinity. That's what we have to show. Now, what do we have to do in order to prove that? Well, we have to demonstrate that the definition is satisfied in this case. So, i.e., when given an epsilon, given any positive epsilon, whenever somebody says, well, make the sequence elements be 1 centimeter away from the limit, or make the sequence elements be a millimeter away from the limit. Whatever small positive distance someone specifies around the limit, that's the epsilon, we need to exhibit an integer n So somebody shouts an epsilon at us. We have to come up with an integer capital N such that for every point after that capital N, so for every small n bigger than the capital N, the inequality is satisfied, that the absolute value of alpha an plus beta bn minus the limit alpha a plus beta b, this has to be less than epsilon. Okay? So it's a very good idea when you're presenting a proof like this is to make it clear exactly what's going to be going on. Okay? So we're declaring at the start what it is we're trying to prove. So we want to prove this thing in the red box. Okay? Well, for the moment, because we're going to have to prove something about this absolute value, what I want to do is just work a little bit, just do a bit of algebraic manipulation on this absolute value. Okay? So first, we'll examine I'm going to label it all as, say, with an asterisk, just to save myself rewriting it all out all the time. So we'll examine the absolute value of the difference up here and rephrase it in terms of absolute value of an minus a and absolute value of bn minus b, okay? Because those are the two things that we can control. Because we know an converges to a, and we know bn converges to b. So we know how to make these two quantities small. We can make these two absolute differences small. So how can we use the fact that we can make them small to enable us to make this more complicated absolute value small? Well, when you begin to examine this, so it's alpha an plus beta bn minus alpha a plus beta b. Right, that's the quantity star, that's the absolute value star we're trying to deal with. Well, at the moment, the an is separated from the a and the bn is separated from the b. So first of all, we just do a simple rewriting of it to bring the an and the a together and to bring the bn and the b together. So I'm just expanding the brackets, collecting the terms, I'm taking out the factors alpha and beta. Okay. So there's the alpha an here minus alpha a here. So you have alpha an minus a. The beta bn here, the minus beta b here. So that gives you overall beta times bn minus b. Now that's moving towards what I said I want, because now at least I can see clearly now here the quantity an minus a and also the quantity bn minus b. And those are the two things, or at least their absolute values, that I know how to deal with, because I know how to shrink them down. I just have to go far enough. If I want to make this small, I just have to go far enough out along the sequence an, and I know this will be as small as I want. And similarly for the other one. But of course, it isn't just that this is alpha times this and beta times this. I'm taking its absolute value. So how do you deal in general? So this is just like a side reminder. If you're dealing with absolute value of x plus y, how does that relate to the two separate absolute values? Absolute value of x and absolute value of y. So how does that absolute value relate to these two? How do you fill the gaps? Anybody remember or can identify the key thing? I should have written them out in a line, so I didn't mean to. So if you've got absolute value of x plus y, absolute value of x, absolute value of y, so there's two gaps here. What goes in the gaps to make a sensible statement there? Sorry? Be brave, shout it out if you... Is it equals? And what goes in the second gap? Plus. Well, that would be true if they were both positive. But say if x was 5 and y was -7. So on the left-hand side, 5 minus 7 is -2. So on the left-hand side, you got 2. But then if you say it's equal to 5 plus 7, you got 12. So you're saying 2 is 12. So there's a way to fill these gaps so that it'll always be true no matter what values of the numbers x and y. It's called the triangle inequality. Does that ring a bell? The absolute value of x plus y, it is related to the sum of the absolute values, but the relationship, it's always less than or equal to. Less than or equal to. So this is called the triangle inequality. It's true in more general situations for when, actually you're doing your linear algebra at the moment. So it's true if x and y are vectors, and these straight lines is denoting vector magnitude, the length of the vectors, then this is true. It's the same statement about vectors, or same notation. So it's a kind of a, we're going to use it here as it applies to numbers, but it's a more general principle that applies in lots of different areas. But certainly true for numbers, for all x and y, for all real numbers x and y. That's the context we're going to use it. So an absolute value of a sum is less than or equal to the sum of the absolute values. That's what it says. So we're going to apply this here. Because this thing here, which we want to make small, so if we want to make it small, then we can do that by bounding its absolute value. And the constants alpha and beta, we can move outside as well. Let me get this statement. So this absolute value, which we're focusing on, this star, we have to show that that's less than epsilon in order to prove the convergence of the new sequence. Well, we know that that absolute value is less than this. Well, this is the key observation, okay? Because we know that the sequence AN converges to A and BN converges to B. So we know that this absolute value can be made as small as we wish, and so can this one. And we just want to make them small enough, make these two absolute values here, absolute value of AN minus A and BN minus B, we want to make them small enough so that the thing we're interested in, the absolute value star up here, make it so that that is strictly less than epsilon. Okay. So we'll call that quantity 1, quantity 2. So we need to make 1 and 2 small enough so that star is less than epsilon. Okay. So I'm going to some effort here to set things up. As you're kind of like playing golf, it's like kind of lining up the ball and the hole and getting everything lined up, and then we're just going to knock it in. Okay, so I'm going to great lengths to kind of say what we're going to do and point out what it is we have to do, and now we'll go ahead and do it. So how small do we make it? How small do we have to make 1? How small do we have to make 2? So that when you plug in those values here, you get something epsilon on the right-hand side. Well, since AN converges to A, there exists a point N1 in that sequence. Remember, we can make this absolute value as small as we want. And since B, I'll leave gaps here. So I'm leaving a gap here on the right-hand side of that inequality. And I'm leaving, we'll make the same statement about B. Of course, B is a different sequence. It may converge at a different rate. So there'll be some other point, capital N2, such that the absolute value of Bn minus B is strictly less than something. Now, I can choose any quantity here at all. So I know they're convergent. I know I can make them as small as I want. Anybody got any, what values, anybody see the answer, so to speak? So the puzzle is, what quantities go here so that when I put them in as upper bounds for this, for 1 and 2 in this expression, that my star is less than epsilon. It's just kind of like a jigsaw puzzle now. You just have to slot the pieces together. Any suggestions for these two? Well, it's going to depend on epsilon. So if I want to make star less than epsilon, these two values have somehow got to talk about epsilon. I've left gaps out in front of them. We don't want to take, if I just chose epsilon, then this quantity over here would end up being alpha, absolute value of alpha times epsilon plus absolute value of beta times epsilon. But I just want epsilon to be in the right-hand side. So I want to fiddle with these values here so that when I plug them in here, I just get epsilon. Yeah. So I basically just want to generate epsilon over 2 here, and generate the other half of epsilon over here. So in the first part, generate epsilon over 2. The second part, generate epsilon over 2. So I want to take some multiple of epsilon over 2 in both cases, but I want a 1 over absolute value of alpha there, and a 1 over absolute value of beta here. Now I'm free to do this, remember, because these sequences are convergent, so I can make these absolute values as small as I want. Well, I'm saying I want to make them this small in both cases. And what I've gone to, labored the point somewhat maybe, but to try and explain why it is we choose these values. These values are chosen so that when I plug them in here, I just get a simple epsilon here, and I've done what I declared I had to do in the red box here. Now, what did I say in the red box? I said, given an epsilon, we have to find a single point n. And after that point, we want the absolute value star to be less than epsilon. Well, I've got 2 points here, an n1 and an n2. That's the same move as we had in the previous proof. How do I ensure that both of these inequalities hold? And the first inequality holds once you get past position n1. The second inequality holds when you get past position capital N2. So you just have to ensure that you're past both of them, that you've gone past the larger of the two. So now, if n is greater than or equal to capital N, I'll just let capital N be the maximum of n1 and n2. So if little n is past or beyond capital N, then I know that both these inequalities here are true. So if n is greater than or equal to capital N, then both the previous inequalities hold. So they're both true. And so the inequality star is going to be less than, well, it's going to be strictly less than, because star is less than or equal to this combination here, but I'm putting a strict upper bound on these two parts here. So it's going to be strictly less than alpha times 1 over absolute value of alpha epsilon over 2 plus beta times 1 over beta times epsilon over 2. Of course, that's all equal to epsilon, because the alphas cancel and the betas cancel, and you've got half of epsilon plus a half of epsilon. So here, we've done exactly what it is we declared we had to do at the start. In the red box at the top of the first page, which you'll have in front of your notes, I said basically, if somebody gives us an epsilon, we have to find a point, capital N, so that the quantity star was strictly less than epsilon. Well, here it is, I've done it. Somebody shoots an epsilon at you. We know there exists an N1 and an N2 with these properties here. And if we let capital N be just whatever the larger of the two is, then that's our point, capital N. And after that point, once the index is beyond that point, star is indeed strictly less than epsilon. Okay? So we've done exactly what we said we had to do. We've satisfied the definition for convergence. So we've proved the theorem. So this is the definition. This is the definition of convergence of our new sequence, alpha an plus beta bn, to the limit, definition of convergence of that to the limit alpha a plus beta b as required. That's what we had to do. So that's the end of the proof of part one. So we can say, hand on heart, absolutely, that linearity case now of the algebra of limits theorem is true. Okay, because we've provided a rigorous argument which uses the definition of convergence, and every step is carefully justified either by algebraic manipulation or linking together our assumptions using the definition of convergence and putting it all together to get to the required conclusion. Now, sometimes, when some people present the proof, or if you look up this proof in some books, the proof starts here. No, sorry, the proof starts here at this word since. So someone says, prove this, and they say, okay, well, since this converges, we can make this difference less than this, and since this converges, we make this difference less than this, and then you hocus pocus, you wrap it all together, and you get the conclusion. And your first immediate question is, well, why did you choose this to be less than this strange-looking thing, and why did you choose absolute value of bn minus b to be less than this? So what I was doing in the preamble here was kind of explaining, that we're focused, declaring what it is we had to prove, focusing on this inequality, relating it to our assumptions, relating the absolute value star to the things that we're making assumptions about, and then that kind of suggests it very heavily that these are the values we choose. We make these inequalities less than these bounds, and that will make our star less than epsilon. Anything I could clarify at this point about it for you? Anything you'd like explained again there? Okay. So now we just want to repeat the whole thing for the other cases, for the products and the quotients. Repeat it in much the same spirit, but maybe not exactly. I mean, this proof dealt in detail with the definition of convergence. Remember, in mathematics, we're always looking to build results on previous results. Okay, we're always looking to make our results work for us, and to not always have to go all the way back to first principles to prove things from the original definitions. Okay, so we'll do a little bit of that here in a moment. So for the product case, first we'll prove a special case. So I'm not going to prove the general form of the product proof. First, I'm just going to prove a very special case, and then we'll put this special case. We're actually going to use the linearity result we've just proved. We're going to combine the special case with the linearity case we've just proved, and that will quickly get us the general form of 2. The special case I'm going to do is I'm going to suppose I've got 2 sequences, AN and BN. Now, what could be special about their convergence, especially as it relates to products? Well, the special numbers related to products are 1 and 0, I guess. You multiply something by 1, it doesn't change. And if you multiply anything by 0, you always get 0. So it's either going to be, I'm assuming they converge to 1 or 0. Well, for this case, the special case we want to look at first is where they both converge to 0. Okay? So they're both converging to the same thing, and that thing is 0. Okay? Well, given any positive value of epsilon, and I'll start to speed up a little bit here, but not speed up in writing, but give briefer explanations. If you're given any positive value of epsilon, we know there exists n1 and n2 such that if n is bigger than n1, the absolute value of an will be less than, I'm going to choose root epsilon now. And if n is greater than n2, I'm going to want bn to be less than root epsilon. So again, I'm choosing special upper bounds based on epsilon. Why am I choosing the square root? Because I'm going to multiply them together, and that will give me just the plain epsilon that I want. Okay, and notice now that if our index n is now bigger than capital N, and you know what capital N is? Capital N is the maximum of n1 and n2. If that's the case, then both these inequalities hold. So the absolute value of an times bn, I'm trying to prove this converges to 0. So I want to prove that if I go out sufficiently far along the sequence that this is less than epsilon. Well, I know it's equal to the product of the two absolute values. The absolute value of a product is the product of the absolute values. But I know the first one, because I'm beyond both n1 and n2, I know the first one is less than root epsilon, as is the second factor. Okay? So both the absolute values are less than root epsilon, so that means their product has to be less than epsilon. So overall here I've got this absolute value is strictly less than epsilon. That's the statement I'm extracting out of this. Okay? So somebody shot an epsilon at me. Here's how I construct my capital N. I know it exists because it comes from the existence of capital N1 and capital N2. And this capital N has the required property that if the index little n is bigger than capital N, then the absolute value of the product is strictly less than epsilon. And what's that statement saying? That statement is saying that the product an bn converges to 0. Because it's saying I can make it as small as I want. Somebody says, make it this small. I choose my n in this way, and lo and behold, it is that small. So we can make it as small as we want, so it's converging to 0. So that is, my pen's about to give up on me. That is the an. Okay, I'm gonna have to switch to red. My an bn converges to 0 as n converges to infinity. So that's a special case of the product rule. If your two sequences are converging to 0, their product converges to 0. And we had to wrestle with the formal definition in order to do that. That's not too bad. But now I can switch to the general case of the product form of the algebra of sequences theorem without having to go without having to engage again with all these epsilons and n's. I can just do it now using the special case and using part one. So for the general case, we combine this being the special case. For the general case, we combine this with part one above. So if AN converges to A and BN converges to B as n goes to infinity, so those are my two general convergent sequences. Well, first of all, notice this is equivalent to, see, if I want to use the special case applies to sequences that converge to 0. But if AN converges to A, that's the same as saying that AN minus A converges to 0. And BN minus, that's a long minus sign, just a minus sign, BN minus B converges to 0. Sorry. I kill myself one of these days with all these wires. So if given any two convergent sequences, lo and behold, you know, really, you can just rephrase it, subtract a suitable constant, subtract the limit, and you've got a sequence converging to 0. So by the special case, we know that the limit of the product of these two is equal to 0. That's the special case. If your two sequences converge to 0, the product converges to 0. So I know the limit of the product of these two converges to 0. Now, what I want is that the limit of AN BN is equal to A times B. So is that result hidden in here somehow? Well, I can restate this result in a few different ways. First of all, I can multiply out this bracket here. So all I'm doing at this step, so i.e. if the first equation is true, then the second must be true, because all I'm doing is multiplying out the bracket. AN BN minus A BN minus B AN plus A times B, so you got the minus A times minus B. Well, now what am I looking at now? Now I'm looking at the limit of something is 0. But what's the something? The something is an example of a linear combination of convergent sequences. It's this sequence plus this sequence plus this sequence plus this sequence. Okay? So using part one, I can break up this linear combination. Okay? So i.e. by using part one of the theorem, which is the linearity, this is the same as saying that the limit as n goes to infinity of AN BN minus, now remember, the A is just a fixed constant. So that can come outside the limit BN, and the B can come out of this limit, minus B times the limit as n goes to infinity of AN, and lastly plus the, no, just plus, well, A times B is just a fixed constant. So I'll just leave that as A times B equals 0. Getting a bit squashed there. So I break apart my limit there using the linearity. Because what it is, it's a limit of this plus this plus this plus this, 0. So I just break it all up and say the limit of the sum is just the sum of the limits. And any fixed coefficients can come outside the limit sign as well, because that was part of the linearity results. So here the A and the B are playing the role of the alpha and the beta in the linearity result. But this statement, well, I've still got limit as n goes to infinity of an times bn. That's what I'm trying to find out what this value is. But I know what the limit of bn is. That's just b. And here I've got b times the limit of an. Well, the limit of an is a. And I've got plus ab here, this plus ab at the end. So I've got minus ab plus ab. So overall, I've got minus ab. Just push it to the other side, and we get exactly the conclusion that we're after. The limit of an times bn is equal to ab. That's exactly the result we were trying to prove. That's the general form of the product rule. So I proved a special case. Special case was just the sequences converging to 0, and then combined that with the result I already had, which was the linearity. Question? Sorry? Yeah, but BA is the same as AB. It's just two numbers, isn't it? And it looks nicer on the page if A is first. A comes first in the alphabet, doesn't it? So I should write it like that. No, but yeah, no, it's important to recognize these are just real numbers being multiplied together. So yeah, I think it just arose because I took the B outside there, so it's right. Yeah, it's the same thing. Okay, any other points? Now we just got time to do the quotient case, the quotient rule. But again, we're going to build it up making use of what we've already got, okay? Because we've already proved the product rule, well, a quotient an over bn, really that's an, notice that if you did have this quotient an over bn, that's the same as an times 1 over bn, isn't it? So actually, I don't need to deal with a full general quotient like the thing on the left. All I need to prove the result for is just the reciprocal, 1 over a sequence. So if I can prove that 1 over bn converges to 1 over b, then the full quotient an over bn is just a product of these two things, and that will already be covered by the product rule then. If the an converges to a, and if the 1 over bn converges to 1 over b, then the product of them will converge to a times 1 over b, which is just a over b. So actually, given that I've already proved the product rule, actually all I need to prove now is the quotient rule for the special case of 1 over a sequence, okay? So since we've proved the product rule, we only need to prove this reciprocal result, that 1 over bn converges to 1 over b if bn converges to b. So if bn converges to b as n goes to infinity, I want to prove that 1 over bn converges to 1 over b. So given epsilon greater than 0, kind of repeating myself now, but it helps to make it clear what you're trying to prove. Given epsilon greater than 0, we need to find the point capital N such that if n is bigger than capital N, the absolute value of 1 over Bn minus 1 over B is strictly less than epsilon. That's what I have to prove. So let's try and find that n. Now, of course, you find the n by controlling the size, by what we need to do is control the size of this absolute value. Knowing that we can control the size of Bn minus B. So I can control the size of Bn minus B, and the question is, does that mean that I can also control the size of 1 over Bn minus 1 over B? It would seem reasonable, because Bn minus B is nearly the same as 1 over Bn minus 1 over B. Well, how exactly is it the same? Or how exactly does the difference relate to the difference of the reciprocals? That's the question. Well, one kind of automatic response when you see two fractions, one of the things that might pop into your head is you see two fractions, you try and squash them together. Try and just express it as one fraction. So you got the absolute value of the difference. I mean, what single fraction is that? If I've only had one horizontal fraction line, what fraction would I write down? Well, you want to express the difference as a single fraction, so you need a common denominator, which would be Bn times B, and then you'd be looking at B minus Bn. Wouldn't you? That's just adding together the two fractions, give you that single fraction. Oh, but there's my absolute value of Bn minus B. Because this absolute value, an absolute value of a quotient like this is just the quotient. Yeah, I can write this like this. And this here is Bn minus B. The absolute value of a quotient is just the quotient of the absolute values. And so here's my Bn minus B. There's the thing that I can control. So if someone shoots an epsilon at me, I know I can make this as small as I want. I can make the top part as small as I want. Now the problem is, I'm trying to make the whole thing small, but there's this thing in the denominator. So if I'm trying to make the whole fraction small, what could cause me problems is if this quantity in the denominator itself gets small. So if the quantity in the denominator of a fraction gets small, that forces the whole fraction to get big. So dividing by something small gives you a large answer. So while I can simultaneously make the top as small as I want to also prevent the bottom from becoming too small. Okay. Well, how do we prevent the bottom from becoming too small? It's 3:47. I don't think I can do that in 3 minutes, or it'll just be a rush through, and people will be thinking of their buses and they won't. So let's just pose the question. So question I, and so by I mean you. I know I can make Bn minus B small, and that will help to make the overall fraction small. But the question is, but how do I stop the absolute value of Bn times B, the thing in the bottom, from getting too small? Because if your denominator gets too small, that will make your whole fraction too big. So that's the question. So, okay, I didn't get through. So we'll deal with that next Wednesday, or you can try and puzzle it out or look up the proof of it in the meantime. But we'll discuss the proof of it next time. But it does use the results we've proved already. We've already proved all the necessary ingredients for it.